Drop an apple, a set of keys, or a coffee mug, and it hits the floor. Why does that happen? The standard answer we all learn in grade school is gravity. We're taught it acts as an invisible force, grabbing objects and pulling them straight down toward the center of the Earth. That model comes straight from Isaac Newton. His equations mapped out a clockwork universe built on this idea of physical attraction, and for centuries, it accurately predicted almost everything we could observe. Despite how intuitive this pull feels, Newton's force model eventually encountered a physical reality it could not explain. Newton's math works if you want to fire a cannonball or build a bridge. But when early astronomers tracked the planet Mercury, the math reached a limit. This diagram compares the two paths. The smooth ring is where Newton's laws predicted Mercury would go, but the erratic, shifting line shows what actually happened. The planet drifted off course, tracing an irregular pattern that no gravitational force could account for. Because the laws of a pulling force could not explain the movements within our own solar system, physicists realized they had to rethink the nature of space itself. In 1915, Albert Einstein solved the anomaly by discarding the concept of a pulling force. His first step was proving that the three dimensions of space we move through and the single dimension of time ticking forward are not separate things. They are woven together into one unified background. This unified four-dimensional structure is called spacetime. Massive objects like stars don't emit a pulling force. Instead, their immense weight sags and stretches the physical geometry of spacetime, creating deep, curved valleys around them. When smaller objects like planets travel near these stars, they don't get pulled. They simply roll along the curved indentations created by the heavier mass. To us, that rolling motion looks like an orbit. The Earth orbits the Sun because it is moving along the straightest possible path through a curved section of reality. It's hard to perceive this curvature because we are physically inside it. Imagine a line of ants walking across a very large watermelon. If you ask the ants, the ground feels flat, and they are walking in a straight line. But from the outside, looking at the entire melon, we can see the geometry of the surface forces them to travel in arcs. We are the ants. What we feel as the weight of gravity is simply our bodies following the invisible curves of spacetime. Because space and time are physically linked, bending the space around a planet also stretches the time around it, an effect known as time dilation. The math dictates a specific rule. The closer you are to a massive object with strong gravity, the slower your clock will tick. This creates a glitch in our daily lives. The atomic clocks on GPS satellites orbit high above the Earth, where the planet's gravitational dent is weaker. Because of that altitude, their time ticks slightly faster than the clocks resting here on the surface. This split-screen counter shows the difference. If software engineers didn't use Einstein's relativity equations to slow down the satellite clocks and force them to match Earth time, the margin of error grows. Without that fix, your phone's GPS would lose accuracy by several kilometers every single day. General relativity operates as a mechanical rule of our universe. Our modern global infrastructure relies on the physical fact that gravity alters the speed of time. Einstein's field equations were so precise that they mapped out cosmic phenomena decades before humanity developed the technology to confirm them. The math pointed to specific spots where space-time curvature is so steep that not even light can crawl out. Long before anyone ever photographed this blurry orange ring in 2019, Einstein's geometry proved that black holes had to exist. The equations also showed that when two of these massive black holes collide, the violence of the impact would send physical ripples outward through reality, creating what we call gravitational waves. It took exactly 100 years of technological progress for scientists to engineer the LIGO facility, an instrument with concrete arms sensitive enough to finally detect those ripples passing through Earth. Sitting at a desk with a pen and paper, a human mapped out the most violent extremes of the universe, simply by calculating its geometry. Yet this elegant system contains a flaw. General relativity dictates the motion of massive structures like stars and galaxies, but it fails to apply to the microscopic world of atoms. At that tiny scale, relativity clashes with quantum mechanics, the physics that govern chaotic, unpredictable subatomic particles. the smooth curves of space-time stop working. Uniting these two contradictory realms into a single cohesive theory of quantum gravity remains the primary challenge in modern physics. Think back to that object dropping to the floor. Watch it again, but with a new perspective. It is not being dragged downward by an invisible tether. We simply exist in a universe where the bulk of the Earth beneath our feet bends the geometry of space.